last time we learned how to build interactive proofs for counting problems. Okay. Actually, we started with a much more humble goal, which was building interactive proofs for the problem of demonstrating that a Boolean formula is not satisfiable. Okay. And where you don't have a short certificate, but there is an interactive proof that works for that. What was the name of the protocol that we used? SumCheck. Okay. So SumCheck was the main subroutine of that interactive proof. An interactive proof, you can think about it as made of two parts. One is an arithmetization that transforms a question about the Boolean formula to a question about a low-degree polynomial, specifically summing the low-degree polynomial over a Boolean hypercube. And then we used the SumCheck protocol to convince the verifier that that low-degree polynomial has a certain sum over the Boolean hypercube. And then we went back and kind of said, well, we can actually arithmetize a little bit more carefully so that the formula and the polynomial actually agree everywhere in the hypercube. So we actually got for free much more than unsatisfiability. We got as much as sharp sat, okay, which is deciding the correct number of satisfying assignments for a Boolean formula. Okay, so that in particular shows that p to the sharp p, okay, so all problems that are decidable in polynomial time with access to a sharp p subroutine has interactive proofs. Okay, so today we're going to go even further, okay, and we're going to show how to construct interactive proofs for all polynomial space computations. Okay, so we already encountered the class of polynomial space computations in the first lecture. In what context? What did we do with it? Yeah.
We showed that IP is contained in Pspace.
Right. So we showed that to the extent that interactive proofs are powerful, they're no more powerful than Pspace, meaning that they will help us decide all kinds of crazy and exciting languages, but not beyond those that are contained in Pspace. So if we are able to show that every language decidable by a polyspace machine has an interactive proof, then we would have shown an equality between the two classes. Pspace equals IP. Notice that this equality, which is, let me write it here, I'm going to prove today. It's rather surprising because what's on the left looks very different than what sits on the right. Right? Sort of here on the right, you have this sort of strange class of languages decidable by polyspace machines. Okay, and here you have some other notion of efficient proofs that involve interaction and randomness. Okay, and yeah, so it should be like a surprising theorem. Okay, so let's get started. Questions so far? Okay. So this theorem is actually due to Ali Shamir from '92. Though the proof that we'll see today is actually a simplification that came out shortly after Shamir's paper. It's due to Alexander Shen the same year. Okay, so we'll see his proof for this statement. Now, the high-level approach for this theorem will follow a similar recipe. First, if we want to construct interactive proofs for an entire complexity class, then what is our first step? Yeah?
Figure out a way to represent every problem in that class?
Yeah, but I don't want to do, there's many problems in that class, right? So one way to handle an entire complexity class is to choose a complete problem. Okay, so the first thing we need to remind ourselves, in case we don't know already, what is a complete problem for Pspace? Okay. This doesn't mean that if a class is not known to have a complete problem, you can't do anything about it. It just means that it's more convenient if you have a complete problem, right? Something concrete to work with. So, so in a state of fact, that there is this problem, TQBF is Pspace complete. So now we're going to define what the problem is. Okay. Okay, so let's spend a few minutes talking about this problem. Later, we'll construct an interactive proof to decide this problem. So the notion that this problem is about is the notion of quantified Boolean formulas. So a quantified Boolean formula, abbreviated QBF, is an expression such as the following. For every x1, there exists x2, such that for every x3, there exists x4, and so on and so forth. At some point, you run out of variables, and you say, maybe for every xn, okay? And then you put after that some Boolean formula, okay? x1 through xn. Okay? So, just a second. Thank you. So what does this mean? It means that what we're asking is whether it is the case that if you plug in 0 and 1 in xn, you can find some xn minus 1, such that if you plug in both 0 and 1 for xn, and you continue like this, at the end, you get some value, right? So this expression is a bit. Do you agree? It's either a bit that is 0 or 1. Okay, so this expression either holds or doesn't as a logical statement. Okay. Now, the language TQBF is the set of expressions, maybe I'll call it capital phi to mean an expression of this form, okay, that are true. Okay, so I can write down an expression, it either has value 0 or 1, and the language TQBF is the ones that evaluate to 1. Okay? Okay, so, and this problem is Pspace complete. If there is time at the end of class, we'll briefly look at why it is Pspace complete. Yes?
The last row, shouldn't it be like arbitrary?
Yeah, so this one, it will be either for all or exists, depending upon what is the parity of n. Also notice that one can consider sort of this type of problems where some of the variables are left free. Here we'll only consider so-called totally quantified or fully quantified Boolean formulas where every variable has been quantified by either for all or an exists. Okay? Okay, so for now, let's just take on faith that this problem is Pspace complete, and as I said, maybe towards the end of class, we'll see why. Now, our approach is going to follow a similar recipe as last time. We're going to proceed in 2 steps. What is the first step? Yeah?
Arithmetize the problem?
Yeah, we're going to arithmetize the problem. Now, it looks a bit different than last time, so we need to figure out how to arithmetize it, but we will arithmetize it, and then we'll get some problem about some polynomial, okay? And the next step will be to come up for an interactive proof for that problem about that polynomial, okay? So let's say, design an interactive proof for the resulting algebraic problem. Okay, so at high level, the proof was going to have sort of similar sort of structure as last time. Okay, so that's sort of comforting. So let's talk about the arithmetization. How do we arithmetize QBFs? Well, a QBF has 2 components, right? It has the formula itself and the quantifiers. We have seen how to arithmetize formulas, right? We've seen it last time. We can start from a 3CNF, right? With n variables and m clauses. And we have seen at least two ways of mapping a 3CNF to a polynomial, right? Here, which of these methods, or whether you need other methods, is mostly a matter of trial and error, okay? But if we follow our intuition, which of the two methods that we've seen last time may make more sense to use? Yeah? Yeah, the more precise one, right? Because here we're not trying to decide whether something is 0. We're really trying to understand what is its value, right? And so the latter arithmetization that we saw last time preserved exactly, could you please close the door? Thank you. Preserved exactly the value of the formula everywhere on the hypercube, okay? So we're gonna map this into a polynomial, p x1 through xn, okay? That's gonna have degree 3m. Okay, and just to remind you, as an example of how it looked like, if we have a clause that looks like x or y or not z, then such a clause, it would be mapped to 1 minus x, 1 minus y times z. Okay, so that was the mapping that we saw last time. Oh wait, so right now, let's say that sort of the first part of arithmetization, we're going to just take this part and just replace it by an arithmetic circuit that realizes the polynomial p. Okay, but we have a few other things to do here, right? So, and also maybe let me write the main property of the arithmetization is that for every a1 through an in 0, 1, it holds that phi evaluated at that point equals p evaluated at that point. Okay, so that's kind of what happens when we make this mapping. So now for the quantifiers, what should we do? We want to somehow find algebraic equivalence for them as well. Yep.
So it's like a for all, you multiply it, evaluate it at 1 and 0.
Yeah, it's a reasonable place to start. Let's say that we have something like, let's look at the very end, okay? Say that we have for all xn, and then we have the expression x1 through xn. Okay, and say that we want to arithmetize this very simple case. Well, we're going to map it to product xn ranges over the two bits, 0 and 1, okay, of p x1 through xn. Now, let's just make it explicit. What is this? Is px1 through xn minus 1, 0, times px1 through xn minus 1, 1. Now, this expression is supposed to kind of preserve oneness or trueness if this one is true at both xn equals 0 and xn equals 1. But this is precisely what this is doing, right? So remember that the polynomial evaluates to the sort of field element 1 whenever the formula is true, right? And if we evaluate it at 0 and 1 and we multiply it together, we preserve the oneness of this, okay? So this feels like the right thing to do. Okay, and whenever you encounter a for all, you treat it as such with the corresponding variable. Let's look at there exists part. So maybe this one is less obvious, but it will be also not hard. What do we do with exists? Yep.
Maybe you could reduce it to the for all case, like not turn it for all.
That's basically what we're doing here. We're going to reuse this gadget. Notice that here we were implementing the OR, right? So it's just like we're doing the OR of two things, right? So we are repeating this gadget of 1 minus 1 minus times 1 minus, right? Which is exactly sort of applying the Morgan's laws to the end, right? So we're going to just dream up some other symbol for that, just for shorthand. So we're going to sort of flip the product on its head, and we're going to define this symbol to mean precisely that. We write 1 minus, parenthesis, 1 minus p, where now we plug in 0 for the last variable, times 1 minus p, and we plug in 1 for the last variable. Okay, so again, it's exactly this gadget. Okay, and we're just defining so this operator to do that. Okay, so maybe let me put here, these are definitions. Okay, so it should be clear that therefore, if I write an expression such as that one for all x1 that exists x2, for all x3 and until for all xn, and I write this expression should, which is either 0 or 1, should precisely equal the expression that I get, the value that I get if I apply all these operators to the polynomial that we obtain from the formula. Do you agree? Like this is a value that is either true or false, and this is a value that is either 0 or 1. Okay, and these two sort of equal if you identify true with 1. Okay. All right. So now we have arithmetized our problem. It's kind of unclear whether we can do something about this, but it is a problem about polynomials that preserves our problem. Do you agree? Okay. Now, this problem that now we need to solve has some appealing structure. In particular, you see that it kind of proceeds variable by variable, which is rather analogous to what was happening for the sum check protocol. In the sum check protocol, we were interested in a sum for a1 through an of p a1 through n. But I can write this sum as sum over a1, sum over a2, blah, 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 sum over an, p of that, right? So the fact that we were proceeding variable by variable was due to the nested structure of sums. Okay? Now I do not have anymore a sum, and then a sum, and then a sum, and then a sum. I have some operator, then some other operator, and so on and so forth. In fact, it's actually products. Okay? All of these involve some form of products. Okay? However, by analogy to what we learned last time, it seems that it is only natural to try to exploit this nested structure. If we could, with some number of rounds, maybe one round, reduce this expression to a smaller one that involves one operator less, then we could just kind of inductively proceed. Okay? So let's write that is. So natural idea. Adapt the sum check protocol to deal with operators. Okay? All right, so I'm going to say that that doesn't work, okay? And there's we will do something that deals with operators, but directly it doesn't work. So there's a problem, okay? If I just say, okay, I have some way of peeling off the first operator, send me a polynomial just in the variable x1. Can you see any problems with the prover sending me the polynomial in the single variable x1 that represents whatever is left after I peel off the first operator? Yeah?
The degree is too high.
The degree is huge. Think about it. x1 as a variable has a long journey to make it until the end, right? It gets multiplied here, and its degree doubles. Then it gets multiplied again, and its degree doubles again. And it continues like this until the very end, right? At the end, it disappears as a variable because we evaluate it at 0 and 1. But if we peel off this, you will get a polynomial whose degree in x1 is exponential in n, the number of variables, right? So even if we just consider completeness, or kind of efficiency, right? Sort of if the prover sends the polynomial P1 in x1, which starts at the second operator, then the verifier has no time to read it. Okay, because the degree of P1 is a 2 to the order of n. Okay? Right? So that's problematic. Okay, so the verifier is only allowed to run in time that is polynomial in n and m. Okay, so this is too much. Okay, so what we're going to do about this solution. Suggestions? Yeah.
The degree of an individual variable doesn't matter. Because then, like, 0 to the n is still 0, and like 1 to the n is still 1.
Good. So this is precisely intuition we're going to go after. Okay. We are interested in the value of these functions only on the Boolean hypercube. When variables are either 0 or 1, the degree doesn't matter. Okay? So to some extent, the fact that the degree is accumulating as we go through here, it's more like an artifact of the fact that we're working with formal polynomials. So what we're going to do is we're going to introduce, formally what we have to do is introduce a degree reduction operator. This degree reduction operator will formally cancel, kind of reduce any exponents that are positive to 1. Okay? And essentially what we're doing is we're doing some sort of bait and switch where there was one polynomial before, and now we switch it with some other polynomial that agrees with the previous one on the Boolean hypercube, and we need to make sure the prover is doing so in a consistent way. Okay? So we're going to introduce the degree reduction operators. Okay? Intuition is strong, but this is a very tricky protocol. Okay? So we'll see that now analyzing it, it can be confusing. Okay? But that's the, so we're going to reduce degrees. Okay, so maybe let me spell it out here a bit more carefully. We only care about the values on sort of this Boolean hypercube, right? So, for example, two polynomials such as x1 squared plus times x3 to the 5th plus, I don't know, x4 times x7 to the 6th. This is the same sort of as x1, x3 plus x4, x7 on the Boolean hypercube. Okay? Why? Because when you put 1 as a value and you exponentiate it to the, you square it or you to the power 5th, doesn't matter, right? So if it's 0, it's 0. If it's 1, it remains 1. Okay? Notice these are two different polynomials, but as far as we're concerned, they behave exactly the same way on all values concerned. Notice that here, we are never evaluating any of these polynomials on anything other than zeros and ones. Okay? Okay, so formally, what we're going to do is we're going to introduce a new operator, R sub xi, okay, which is going to be the operator that sort of maps xi to the k to xi in the event that k was actually greater than 0. Okay, if xi wasn't appearing, then it doesn't appear. So the new statement that we want to prove is what? So now we want to somehow say that this is actually not what we're going to look at. We're going to look at some other statement, okay, that involves these other operators. Where do we sprinkle these So I'm going to have three types of operators, okay? The product, the whatever anti-product, and a degree reduction operator. What kind of statement do we have now? Yeah.
If we reduce degree before we pass any polynomial to the verifier?
Yeah, but first we don't have a verifier yet. We need to make sure that no point the degree gets too high, right? What's a good way to make sure that no pointer gets too high? Yeah.
We interleave them in between the operators that we already.
Yeah, we just put them wherever, like everywhere it makes sense, right? So don't put an operator for a variable that has disappeared, but for any variable that is around, put it in. And then there will be some other operator that will kind of double, again, the degree of all variables that are still around, and then reduce all of them, okay? We could put them a little bit less, but it's just easier to put them everywhere because it would be easier to talk about like that, okay? So concretely, you start out with P, which you have obtained from phi, and you right away reduce everything. Some of these things will have degree greater than 1, right? In fact, you might have degree upwards of m, right? M is not bad in principle, it's just that we want to sort of understand degrees as we move through. So immediately we reduce every variable to degree 1. Then we actually have to make some progress on the original problem, so we have a product, so we put it in. Now this product will sort of cancel the variable xn. Now because xn has been cancelled, there's no point to reduce its degree anymore. But all other variables are still around. There is x1 through xn minus 1. So we reduce all of them. So we have r x1 through r xn minus 1, right? Then we have the variable xn minus 1, right, that we're canceling. And we continue like this. And at some point, we have, I don't know, the operator for x2. At this point, only the variable x1 has been around. We reduce it, okay? And we have the final operator over x1, okay? So this is the new statement that we're going to prove. And we're interested whether this statement equals 1, right? Is it clear what we did? We just reduce wherever it makes sense all the time, okay? I could have done it in a sum check protocol, but there was no need because degrees don't blow up. Something that sort of will become apparent in sort of over the period of this course that this notion of arithmetization is as fluffy as it is flexible, in a sense that I can't quite give you a definition of what it means to arithmetize it, but it will just show up in so many forms that are sort of all interconnected. Yeah. Yeah.
So is the reduce operator just multiplying out the terms?
It's like a formal thing. Like you see a polynomial and you go in the exponents and you cross them off and you replace them by 1. Mm-hmm. So it just you can think about it as really like bait and switch. Like you had a polynomial in front of you, you take it, you put it in the trash, and you put instead another polynomial which equals the previous one up to the fact that in all relevant variable appearances, now the exponent is always 1. Okay? So it's really like a different polynomial, like here. Okay? So if you apply the polynomial, okay, here we reduced everything, okay? But if you had applied just the rx1 operator, you will go from here to here, just making this change. Okay? So we're not algebraically transforming the polynomial like we are here. Here. These are algebraic manipulations. There we're just swapping it. Okay? We just say, no, I don't like you, and I'll just put a different one. But they agree on the Boolean hypercube, so that's why it's okay to do that. That's one of the reasons why it's confusing, because it's not like a manipulation, it's like you're just swapping it.
You're taking the unique polynomial of smallest degree that agrees with the polynomial that you had on the Boolean hypercube. So like this is
yeah, that's another way to see that, but that's when you consider all of these.
Yeah, if you take all of them together.
If you take all of them together, that's kind of re-extending there's a function that you care about on the Boolean hypercube, and here it's taking the sort of unique extension. This may or may not help you if you sort of like to think about extensions, but like formally, you're just swapping it, okay, with some other one that agrees on the hypercube, okay? Yeah, thank you, Nick. All right, so that's the new thing that we want to prove. Notice that in the past, we had at some point to pick modulo what are we working, okay? Modulo prime, and we had to make sure that the prime, we pick it large enough for things to make sense, okay? Now, so the technicality, we need to pick Q for our field. How should I pick Q? Right? So before we start actually running a protocol, we need to pick our Q. Let's say from a completeness perspective, how big should Q be? Excuse me? For completeness, yeah. It doesn't matter. Yeah, so any prime would work, including Q equals 2. Because here we're absolutely uninterested in anything that is happening outside 0 and 1. Okay? In the good case, all the good stuff is happening in 0 and 1. Now we also have soundness. And so for soundness reasons, we're going to need to take Q, okay, to be larger than Q equals 2. Okay, we're going to need Q to be bigger. Actually, this time it's going to be much smaller than last time. It's going to suffice to take something that is polynomial in m and n rather than exponential m and n. Okay? So actually the size of Q in m and n will be logarithmic. It's actually not a big deal. In the sum check, it was good enough to take it to be exponential. And it wasn't a problem for us. But just curiously, we can actually take a Q this time that's exponentially smaller. Okay? It's not clear right now why, because I haven't said the statement of soundness, but we'll see later that this is what we need. Okay, so let's start talking about the protocol. Okay? So the protocol will be to go operator by operator until we're at the end, okay? And you see now we have different types of operators, so what's gonna be helpful to think about is think about the protocol more abstractly as a reduction from one plane to another, and then we have multiple cases. Either we are at one type of operator or another, okay? And we just kind of tackle each of these three cases, okay? So we're gonna have an operator script O is in the set a product xi, anti-product xi, or reduction xi. Okay, so we're gonna deal with operators that are one of these types. The total number of operators is, we need to make sure that it's not too large. What's an expression for a total number of operators? Yeah. Seems about right, yeah. So I mean, the way I was counting it was like I plus 1 a squared, right? Because like we have yeah, I think that's kind of, no, like without the square, sorry. We are, at the very end, we have 1 and n, then 1 and n minus 1, then 1 and n minus 2, right? But either way, the point is that it's order of n squared. Okay, that's important, by the way, that we don't have too many rounds. Not just for that, also it will affect later our soundness, okay? Because we'll have some soundness loss at every round, so that tells us how we pick Q. And then at round k, which is between 1 and L. So something to keep in mind that is sort of one of the confusing things about this protocol is that the round number need not be tied to the variable number, right? So in the sum check protocol, when we were in round I, we had something to do about variable I. Right now, when we are in round K, we'll be doing something about some variable xi. Okay, depends, right? You see that now they're sort of different things. So that's why I'm calling it K. Okay, so we're going to have some initial claim. The claim will say, okay, there is a particular bit, vk, and the claim is that if you apply the operators onwards from here until the end, well, there's no phi, there's p. By the way, in general, we're not going to have p here anymore. We're going to have some pk, because sometimes we change the polynomial that we talk about, right? So somewhere into the protocol, we will have changed our mind about which polynomial we talk about. Okay? Mod q. So that's the claim that comes into the protocol. We run out some sub-protocol. And really, the only input to the sub-protocol is just that number, which is a bit. And the sub-protocol will spit out, not a bit, sorry, this is going to be in general in FQ. And we start out with a statement about 1 or 0, right? 1 if we talk about TQBF. But as we go through, we're going to be evaluating things and talk about field elements, okay? So that's a value in FQ. And the new claim is going to start at the next operator, okay? And continue and potentially be about a different polynomial. Okay? All right. And we're going to have the property completeness of this reduction is that if initial is true, then the final is true with probability 1, okay? And soundness will say that if initial is false, then the final is false with high probability. With high probability is something we'll have to control. Now, this is somewhere in the middle of the protocol, and we're just a chain of reductions. It's important at the very beginning that we start out sort of so at the boundaries that we have things that are anchored to true things that we can check. Like in sum check at the very beginning, we start out with a statement about the sum of the polynomial, and then as we go through, we have other statements. And
What is pk and pk plus 1?
some polynomial.
Apply the operators.
Yeah, here we are applying these operators to this polynomial, and here we're applying these operators to this possibly different polynomial. At the very beginning, now we're going to start out with v0 to be 1, and p0 is going to be p. Okay? And at the end, there will be some VL, okay, equals PL, and the verifier will be able to do it. Okay? Just like at the end of the sum check protocol, there is a particular statement that says something that you know about, for example, P, evaluated at R1 through Rn, has a particular value, right? And that's a statement that it could have checked. Okay, this is kind of like the structure of the protocol. And now we want to sort of zoom in and make sure that we know how to handle these different operators, okay? If we can handle all operators and we understand what's happening, then we'll have processed everything. We're almost at the end here. So the setup is it's a non-trivial setup here. Okay, so let's see, what do I get rid of? Okay, at this point, I think we're familiar with QBFs enough, and I'm going to get rid of the definition. By the way, notice that what we're doing is not quite the sum check protocol. It is similar to it in that it has this variable by variable progress throughout the interactive proof, but it is also different. So in particular, the sum check protocol was introduced in a certain paper, and new ideas had to come in to get here. And this notion of degree reduction, you see, it's kind of non-trivial, right? So if you just blindly apply the sum check protocol, you will get a very large degree. Okay, so now we have to distinguish three cases. Okay, let's start with maybe a simple one and familiar. Say that the operator that we want to peel off, called script O k plus 1, okay, equals product of xi for some I. Okay, say that we're in this case. Notice that I need not equal k, right? So in this case, how do things look like? Okay, we have some claim that says vk equals, and then we start out pi xi, because that's the first operator here. Now, what do we expect to see after pi xi? Well, if pi xi now gets sort of canceled out, it means that we have some rxi here, right? Because just before, I mean, this is the last time xi appears, but before it does appear, so we were reducing it. And then we have rxi plus 1, so on and so forth, until maybe there is a this is this is x1. Sorry, x1 through up to xi. Sorry about that. Here we have just cancelled pi. Anti-product xi plus 1, right? And we continue like this. At some point, we get to pk plus 1. Now, pk plus 1 has n variables, okay? Because notice that every time we swap a polynomial for another one, the number of variables is the same, okay? And some of these variables are fixed, and others are free. How many variables do you think I should have fixed? Yeah.
N minus xi.
N minus xi. I mean, we have xi here, right? So we could have only fixed things to the left, right? So I would say, r1 through ri minus 1 have been fixed, okay? And then the others haven't yet, okay? Because you were talking about them here, right? We have xi up to xn. All right, all I've done is I have said we are in this case. Let's take the general expression and just be more concrete about it so we can talk about it, okay? Okay, so we're going to have a protocol, which is going to just be two messages. The prover is going to say something, then the verifier is going to say something. Prover, verifier. So the prover is going to say some polynomial. Let's give a name to it, pk. I'm going to give a tilde. I'm going to put a tilde on it to mean that it's going to send some polynomial in the variable xi. Now, intuitively, what should the honest prover send? So if this is the claim, what polynomial should the prover send? How did it work in SumChuck? we were summing, so let's look at the start of sum check. We're summing over everything, right? And the first polynomial the prover sends is to say, yeah, don't sum over the first variable. Just sum me whatever you have with that variable free, right? Now here, like the first operator is xi, right? So if I remove this operator, what do I expect to see here? Polynomial in xi, right? So, or well, need to be more precise here. Yeah, no, in xi. That's it. Yeah, a polynomial in xi. What is its degree? 1, right? Because I just reduced it here. Okay. Okay. So he sends that. What should I check when I receive it? I should check the vk equals product xi pk tilde. Right? I mean, if that's what he had to send, then at the very least I should check that. Right? Okay. Then I'm going to sample Ri at random, and I'm going to send it to the prover. The next claim is going to be vk plus 1 equals, and then here I have R of x1 up to product xi plus 1 up to, and then at some point here I get, in this case, the polynomial didn't change. We're still talking about pk plus 1. I just have fixed one more variable. So if I had Ri minus 1, now I have Ri, and I continue with xi plus 1. Okay, so just maybe to highlight that we have fixed xi, okay? And here we have sort of lost that guy. So let's analyze this reduction, okay? It's actually gonna it's gonna be easier than you think. So now completeness, let's just formalize what it is that we want, what we just said, that the honest value, the honest polynomial to send is just whatever you get by taking all this stuff, okay? So it's R x1 up to R xi, okay? Product xi plus 1, I continue up to pk plus 1, and I just write all that stuff. Xi and then up to xn, okay? So if I send this, okay, will I pass this test? Yeah, I mean, that kind of by construction, right? Okay, then, okay, the verifier will sample some random thing, and will this statement hold? Yeah, I mean, because, oh, I didn't say how to set it. Vk plus 1 is defined to be pk tilde at Ri. Sorry, forgot to put it. So will this statement hold? Yeah, because, I mean, I sent the right thing, and he's setting the correct statement, right? Oh, wait, so completeness is good. Soundness. Well, I feel that some people are confused. This is a confusing protocol. Looks intuitive, but it's like the soundness is really fishy. Are we at least fine with completeness? By the way, okay, let's maybe make sure we understand something. You may be wondering, oh, look, the variable x1 is around, so why isn't this polynomial also in x1? Can anybody answer? Let's at least we understand syntactically why this is a univariate polynomial. Like if I take this expression, why doesn't the variable x1 appear here? Yeah.
Because you're like, well,
I evaluated it.
producting it out. You're
No, I'm not. That's the thing. I'm not printing it out, right? I'm evaluating it, right? So the other variables are product out, right? For example, xi plus 1 has been product out, okay? But here, the other ones haven't yet, but they don't appear because I have evaluated them, okay? The one variable that hasn't been product out, or been evaluated is xi. That's why this polynomial is a univariate in xi, okay? All right, so this syntactically this makes sense, but it's very confusing, right? Because there are these variables out there that are being product out, right? And the ones that are evaluated, it's very confusing. But as confusing as it is really analogous to sum check, right? So halfway through sum check, what has happened? Some variables have been fixed. One is free. The other one, you're kind of tracing them out, right? Because you're summing over the rest of the hypercube, right? It's exactly what's happening here, okay? Just using different operators. Okay, so please nod if you're comfortable with completeness. Okay, we have some constant fraction of nods. So, okay. Huh? Yeah, no, that's good. To keep a very low bar. So, please ask questions if it's confusing. Okay. So this is basically saying that if the claim to begin with is true, sending this polynomial will preserve its truth regardless of the choice of the verifier when its samples are I. Okay. So that kind of takes care of the completeness condition there. Now, suppose the original claim is actually false, okay? Now, let's give a name to this polynomial, the honest one. Let's call it pkxi. Okay, it's different than pk tilde, which is what the prover sends, okay? Let's define this expression to be pkxi. Now, as a prover, in the soundness case, there are two things the prover could do. Either he sends this specific polynomial or something else. Okay, now let's look at those two cases. Case 1, prover sends pkxi that equals pkxi. Okay? Now, in this case, what happens?
You are assuming that the statement is wrong.
I'm assuming that the statement is wrong.
So we catch it.
With what probability? 1. Okay, we reject with probability 1. Okay, so caught with probability 1. Why? Because we're saying that this statement is false, right? Where pk is this expression here. The first step of the verifier, it completes the last operator and checks whether the original statement is true. So, but it was false. So this is really a very lousy prover strategy. Okay? Now, case 2, the prover sends pk tilde xi that is different than pk xi. Okay? Okay, so he could do that. He could just send some polynomial that is not the one that sort of the honest strategy dictates. In this case, what's going to happen?
So the next step. So now when you picked up Ri, if case 2 happen, you're going to catch him with good probability in the next step.
Or it's not like I'm catching it, it's just that the next claim is false with high probability, right? So, and then it will be, you know, some other rounds problem, right? So then, output claim is false with probability. Okay, or let me just maybe put it the other way, is true with probability at most what?
1 minus 1 over.
Well, I said true.
2 or 1 over the.
Yeah, 1 over q, right? Why? Because we're comparing univariate polynomials. Okay, they are univariate because we just reduced xi here. Okay, so with only probability 1 over q, the prover will be able to proceed to a true statement. With all other cases with large probability, 1 minus 1 over q, the next statement will be false. Okay?
Degree 1.
Sorry?
You said the universe, degree 1.
I'm sorry, yeah. Union polynomial of degree 1, or linear polynomials, yeah. Okay. All right. I have 2 more cases, okay? Okay, but one of those 2 cases is, yeah, similar is, yeah, the same basically. I mean, you can syntactically go through and kind of flip things. I mean, maybe don't flip this one, but flip just that one. but otherwise, it's the same thing. Okay. So we can say 2 here is phi k plus 1 equals sort of this anti-product, and it's sort of the same. Okay, so that's easy. Now let's maybe look at maybe the one of the 3 cases that is a little bit different. Actually, will not be very different. Is how does the degree reduction operator work? Okay, why does it actually work? Okay. So now we have case 3, where phi k, so script O of k plus 1 equals r x I for some I. Okay. Like before, we would like to get a more concrete sense of how the statement, yeah.
Just a question about the first case. So if the output claim is true in the soundness case, like does that mean we've lost any ability?
Yeah, we've lost. So if with probability 1 over q at any round, where either this or that happens, we flip from a false statement to a true statement, and then we've lost. Okay? Now, in particular, at the very least, we need to make sure that L over Q should be small enough, right? Actually, well, L is number of rounds. We'll actually have to do a little bit more than that, okay? Because this case has a slightly larger probability here, but at the very least, we need to make sure at L over Q, because by a union bound, things could go wrong at any round, okay? But we control Q, we can make it large enough to not mind that. Good question. Okay, so now we are in this case where we have the degree reduction operator, and just like before, we want to rewrite the generic statement for this case to have a more concrete sense of how it looks like. So it will look like this: R xi, because that's, sorry, we have vk equals R xi. What's the next operator? Do I know? I don't know, right? Because this RxI could appear a bit kind of anywhere, right? I don't know what's after. Maybe another R, or maybe some other operator. I don't care. So I'll just write O k plus 2. And continue. At some point I get maybe pi xn, r x1 through r xn, and at some point I get to my p, k. And now we want to be sort of careful, sort of, how many variables have been fixed? So before it was really clear, right? we were just about to fix Ri, right? Here I'm reducing xi. And before I mess it up, let me write the answer and we can reason about it, okay? So we're going to have R1 through Rj. Then at some point, we flip over to the non-fixed ones. And I claim that j should be at least I. Okay? Namely that the I that we talk about is somewhere here. Okay? That's sort of, I sits somewhere there. Wait, sort of, ugly. Okay? That's my claim. Does it make sense? Okay. So let's see the protocol. So we want to send, we're going to, again, receive a univariate polynomial. Okay? Let's, like before, call it pk tilde. It's going to be in the variable xi. And what is it that we want to check? So he sends something. We're going to see in a moment what that should be. But what it is that I want to check? I want to peel off this guy, right? So presumably, I want to apply R. I'm going to check that Vk equals, I take Rxi, I apply it to Pk xi, right? And now, but no, this doesn't give me a value. This gives me a polynomial, right? So I can't compare a univariate polynomial to a value. So what else should I do? Yeah.
Check if it's the same as 0 and 1.
I was somewhere here. We have lost zeros and ones. Yeah, I evaluated Ri, the old Ri. Okay, why the old Ri? Because we'll sample a new one. So we're going to sample Ri new and send it off. Okay, so and then I'm going to set Vk. So we're going to look. Let's look at this carefully. I'm going to set Vk plus 1 to be Pk tilde at Ri new. Okay. And my new statement is going to be Vk plus 1 equals. Now I have peeled off this guy, so I have that one. I continue up to pi xn, Rx1 through Rxn, P. And now in this P is a different one, potentially. Pk plus 1, I'll call it. And I'm evaluating R1 through, at Ri, I'm going to put in the new R. Then I continue up to Rj, right? And I continue with the other ones, xj plus 1 up to xn. Okay, let me just try to highlight with colors. What has changed is that here we had a Ri that changed, right? And of course, then we peeled off this guy. So let's understand completeness first, okay? So the good thing to send would be Pk tilde x, when Pk tilde xi equals what? Can I just say this guy? But I should clarify that when you see variables here and also here, you should think about it that it's not like you plug in the variables and then you apply the operators. You first apply the operators and then you plug in the values, right? So, okay, given that that is the case, maybe it will help you come up with the answer. So, can I just send this? That syntactically makes no sense, right? Because it's a value, right? It doesn't have, it doesn't have any variables. In particular, it doesn't have the variable xi, right? So what should I do? I just don't evaluate at Ri. Okay, I just change it back to a formal variable. So what I should send is I start at OK plus 2. I continue, blah, 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 up to Pk. And now I go from R1, and then for xi, I leave xi, not the old Ri. Okay, I put it back as a formal variable, and I continue with the plugged-in variables. Okay. Now, these guys are traced out by the other operators, so they don't worry me. So now I have this variable, okay? Now, let's convince ourselves that if I send this one, then I do get a true statement, okay? Well, let's see. If I send this one, what's going to happen? I am going to reduce it. And then I'm going to evaluate it at Ri, which is what I had before. So when you check this, it will hold. Okay? So let's give a name to this one. This is kind of the correct polynomial. It's going to be pkxi without a tilde. Okay? So that's completeness. Soundness. Okay, so like before, we have two cases. Either a prover, fully knowing that the original claim is wrong, it will still decide to send pk tilde xi that equals pk xi. Then what will happen? So the assumption is that this claim is wrong. If the prover sends precisely this polynomial, and I do this check, what happens? I reject all the time, because kind of formally this thing will evaluate to this guy, right? And then we said it's wrong. So this is caught with probability 1. All right, in case 2, the prover sends pk tilde xi that is different from pk xi. Okay. I sample this Ri new, okay? And then basically I have a claim that says, look at this thing and compare it to that one, okay? Now this guy contains the kind of pk evaluated at Ri new. Right? So this guy is pk evaluated at Ri new. This guy is pk tilde evaluated at Ri new. I am in the case where these two polynomials are not the same. Okay? So the new claim will be true at most with what probability? Maybe 1 over q, okay? But I need to be more careful, because why would it be 1 now? I am a reduced operator, not after reduced operator, right? So here, let's just first say what matters. We're going to say that a new claim is true with probability at most the degree, to be precise, I guess it would be pk tilde minus pk, or either of them really, over q. And what is the degree of pk or pk tilde? It depends, okay? It depends where we are in the protocol. So let's say we're somewhere here. What will the degree be?
M?
Yeah, no more than m, right? How about here? Yeah.
2.
2. Here? More 2s, right? So unless we're in the last case, it's always 2, okay? Otherwise, it's perhaps as bad as m, okay? So, and this is like either 2 over q or m over q. Okay, now we have to tally up, okay? So we have many rounds, and some of them have some probability, others have other probability, okay? So the overall soundness so we are paying the 1 over q case there, how many times? So either of these, how many times? N times, right? Because we have n variables. Okay, so that's n times 1 over q. Plus what? How many of these do we have? Just these guys. N, right? So we have n times m over q, right? That takes care of these guys, right? Plus roughly n squared, and more precisely, I think it's something like sum of I going from 1 to n, I, okay, but whatever, order of n squared times 2 over q. Okay? So in the end, we have something that is 3mn plus n squared, if I didn't mess up my my computations, which is poly mn over q, which is, that's why I said earlier that we need q to be at least sort of some polynomial in m and n. Okay? All right. This is a very non-trivial protocol. So let's try to kind of take a step back and understand what has happened. First, does the verifier in this protocol use any secrets, like in GNI? No, this is all sort of public, okay? But anyway, we'll see in the next lecture, we'll precisely talk about this gap between sort of public and private randomness, okay? But like in the sum check protocol, we get the inclusion, a very strong inclusion, okay? Without using any secrets, okay? Every time the verifier opens its mouth, out comes random coins, okay? That's all the verifier is doing, okay? You think about it, it's a rather trivial verifier, right? Because it's sort of never sending anything, that interesting to the prover. All it's using is the fact that the prover sends a polynomial and has sent it, and then it tests the polynomial on something that is independent from it, okay? Okay, we did use many rounds, so a question is, do we really have to use this many rounds? It's actually a rather deep question about the theory of interactive proofs. But we did use not too many rounds. Polynomial, we said it was okay, and we did use polynomial, okay? Fortunately, the verifier is never doing any work. Every time he's doing is he receives some low-degree polynomial and either sort of applies some products or some sort of degree reduction operator. So clearly, the verifier is never working hard at all. So again, poly in M and N, okay? And finally, from a soundness perspective, you can pick Q to be large enough to make this arbitrarily small, right? And notice that this protocol captured the entire class, the full power of interactive proofs. Okay, so sum check by itself didn't quite make it. We had to come up with this other protocol that is able to handle these alternating sort of types of operators. Okay, and by carefully orchestrating this chain of reductions, okay, one is able to sort of decide any language in Pspace. Now, it might actually be instructive to go back to the sum check protocol, and we did a particular type of analysis and try to recast that analysis also as a chain of reductions. That can also be done, okay? Essentially, what you're doing from round to round in the sum check is reducing from a sum check claim to another sum check claim with fewer variables. And you could have analyzed the sum check protocol in this fashion by just isolating one round and reasoning about whether you flip from false to true, or if you preserve false to false, sort of, and with what probabilities those things happen. Okay, and then you can deduce soundness of the protocol from such a reasoning. Okay. The other thing to notice is that sort of this sort of power arithmetization was rather flexible. Here we were able to just apply it, and it was working. And of course, I set it up this way. But yeah, we'll see throughout the course, this notion of arithmetization will come up all the time for very many different problems. Now, next time, we'll look at specifically at the gap between public and private coins, and we'll look at a result that may be surprising, is that we'll go back to graph non-isomorphism, and we'll show that in using still two messages, so not many messages, two messages, we can come up with an interactive proof for it that uses no secrets, so just public coins. We know there is one with many rounds because now there is Pspace. In fact, before we even had CoinP with just the plain sum check protocol. So we know we can handle GNI with public coins, but that's many rounds, okay? We'll see a technique that will let us handle it with only 2 rounds without using sort of the secret bit, which felt so essential to the proof, okay? After, just to kind of look a little bit further, then we'll have another week on interactive proofs, and and in that week, we'll start discussing sort of delegational computation. We'll start capitalizing on some of these techniques that sort of create speedups for the verifier and use them to enable the verifier to enlist the prover's help to check, say, the computation of a function faster than it could have by itself. Okay? So that's kind of the plan for the week after. Okay, so today was a rather heavy lecture, so let's stop here.